Hey guys, Mr. T here. This is another video. This one is on Hungarian algorithm and minimization using the Hungarian algorithm. So I've been alluding to the fact that we are going to learn about a more systematic method of optimizing or doing optimal assignment problems without using trial and error. Okay, this is known as the Hungarian algorithm, the one that we're going to use, because more complex optimal assignment problems would take too long to solve by trial and error alone or just doing them by eye. The Hungarian algorithm is a series of steps in a certain order that you can apply to optimize assignment problems, which you've translated into matrix form to start off with. Alright, so these are the steps that you are going to use when you're minimizing using the Hungarian algorithm. We start off with minimization because maximization is very similar except for one initial step that you do first to maximize. So with minimization, step 1, in each row of the matrix, you subtract the minimum value in the rows from the elements in that same row. 2, you do the same thing for columns wise, so in each column, subtract the minimum value in the column from the elements in the same column, and that includes zeros as well, so 0 is obviously going to be the minimum value. If your columns have zeros in them, you're not going to do anything because subtracting 0 from something will leave it the same. Step 3, cover the zeros up in the matrix with the minimum number of horizontal and vertical lines. I found that the best way to do this is, instead of just drawing a line through the first zero that you spot, start by drawing lines through any rows and columns that you find that have multiple zeros in them. Start with the most number of zeros in each column and line, then work your way down, say 4, 3, 2, 1, that sort of thing. Don't start off with columns and lines with just 1 0 in them. And as part of step 3, if the number of lines that you've drawn to cover up zeros is equal to the number of rows in the matrix, you skip straight down to step 5. If not, however, you do step 4. If the lines in step 3 was less than the number of rows in the matrix, you need to do this next step 4, which is find the smallest uncovered number. So you covered up a bunch of numbers with your lines. Find the smallest uncovered number in the matrix. Then what do you do with that number? You subtract it from each uncovered number in the matrix, but you add it to every number that is covered by 2 lines. So it has an intersection of horizontal and vertical lines through it. Then you go back through and do step 3 again. Okay, so that's the idea of step 4. You try drawing lines through the zeros again at the end of step 4 by repeating step 3. Once you've done that, repeat of step 3, do step 5, identify a pattern of zeros in the matrix so that each row and column has only 1 0 in it. So it's almost a spatial recognition problem you need to work out in your head. A selection of zeros in the matrix where every row and column only has 1 0 in it. This pattern that you find is the optimal solution, minimization, when you apply it to the original matrix. Okay, so to show this, we're going to revisit the swimmer's problem that we did by eye in the last video. The following matrix shows the time in seconds taken by swimmers A, B, C, and D to swim 100 meters of the strokes: backstroke BA, breaststroke BR, butterfly BU, and freestyle FR. Find the optimal assignment of swimmers to strokes to minimize the total swimming time for the team as a whole. So this is the same matrix from the previous problem. We found an optimal solution just by eye or through trial and error. Let's see if we find the same solution by applying the Hungarian algorithm, and it should be quicker, at least when you are experienced with the technique. So step 1, subtract the smallest element in each row from every element in each row. So looking at row A, 52 is the smallest, so I'm going to take 52 from each element there. Row B, the smallest element is 62. The smallest element is 49, so I'm going to minus 49 from each element in that row. The smallest element in row C is 51, so minus 51 from each element in row C. And row D, the smallest element is not 54, 48. So I'm going to minus 48 from each element. In row D, so to show the result of step 1, I draw another matrix here. 56 take 52 is 4. 59 take 52 is 7. 52 take 52 results in 0. 53 take 52 results in 1. First row done. 62 take 49. 49, 50, 51, 52, 53, 54, 5, 6, 7, 9, 60, 61, 62, 13. 67 take 49 is going to be 18. 59 take 49 is going to be 10. 49 take 49 is going to be 0. 55 take 51 is 4. 64 take 51. 51, 52, 3, 4, 5, 6, 7, 9, 60, 61, 63, 64, 13. I count with my fingers 2. Deal with it. 51 take 51 is 0. 58 take 48 is 10. 60 take 48 is 12. 54 take 48. 48, 49, 51, 53, 54, 6. 48 take 48 is 0. So that is step 1 done. Step 2. Subtract smallest element in each column. From every element in each column. So we do the same process as step 1, but do it vertically this time, starting with the matrix that was a result of applying step 1. So in each column, I need to subtract the smallest element. So in the first column, I'm going to be taking 4. In the second column, I'm going to be taking 7. I'm going to be taking 0, so nothing happens in the third column. I'm also going to be taking 0 in the last column, so nothing happens in that. So the result matrix for step 2. 4 take 4 is 0. 13 take 4 is 9. 4 take 4 is 0. 10 take 4 is 6. 7 take 7 is 0. 18 take 7 is 11. 13 take 7 is 6, I hope. 6, 7, 8, 9, 10, 11, 12, 13, yes. 12 take 7 is 5. And because I'm subtracting 0 from the third and fourth column, they do not change. So that is step 2 done. Step 3, just double check what that step was. Step 3, cover the zeros in the matrix with the minimum number of horizontal and vertical lines. Cover zeros in matrix with min number of horizontal and vertical lines. So I'm going to do step 3 in red on the step 2 matrix. So what I've suggested to you is look for rows and columns with multiple zeros. So I can see 3 zeros here, so I'm going to draw a line through it. I can see 3 zeros here, so I'm going to start with that. Now we look for less zeros. There's 2 zeros in this row. Then I don't have any other uncovered zeros. So that is my step 3 done so far. If number of lines is equal to the number of rows in the matrix, skip to step 5. I drew 3 lines. There's 4 rows, so I don't get to skip to step 5. So I do step 4 now. If number of lines in step 3 is less than number of rows in the matrix, find smallest uncovered number in the matrix, subtract it from each uncovered number, add to every number covered by 2 lines. So step 4. Why is that like that? It's a highlighter. Pencil. Step 4. Smallest uncovered number, subtract from other uncovered numbers, add to numbers covered twice. So the smallest uncovered number from step 3 is 5. So I'm going to draw the result of the step 4 underneath. Numbers covered once are the same. I add the smallest uncovered number to numbers covered twice. That 1 in the top right corner is covered twice, horizontally and vertically, so 1 plus 5 is 6. Uncovered numbers, I take the smallest number away, so 9 take 5 is 4, 11 take 5 is 6, 10 take 5 is 5. I don't do anything with numbers covered by one line, 0, 6, 7. I add the 5 to double covered numbers, so 5. Uncovered numbers I take 5 from, so 1. 5 take 5 is 0. 6 take 5 is 1, and I don't do anything with that. So step 4 has been done. Now I go back and repeat step 3. Cover zeros in the matrix. So I'll stay there, I'll repeat step 3. Repeat step 3 now, which is cover zeros in the matrix with a minimum number of horizontal and vertical lines. So look for multiple zeros first. That's 3 in a row, 2 in a column, 2 in a row, and 2 in a column. So now I have now 4 lines drawn, 4 rows in matrix. So I can skip to step 5, which is identify a pattern of zeros in the matrix. So each row and column has only 1 0 in it. This pattern is the optimal solution, the minimized solution when applied to the original matrix. So step 5 is to find a pattern of zeros. Find pattern of zeros where there is only 1 in each row or column. Okay, so here we use some trial and error, use a little, I don't know, lateral thinking, spatial recognition to identify. I could start in the top left, but let's have a think about that first. If I was to circle the top left 0, I would not be blocking any selection of zeros in the next column because I've got 2 options here, but the only 0 I could possibly circle in the third column over is also in the top row. So really I'm limited to choosing this 0 here in the third column. That would stop me from selecting this 0 in the first column. So that means that, thinking ahead, I actually have to circle this 0 down here, and I might as well go ahead and circle that 0 in the third column because that's the only one I can choose. So really the choices are for the second and the fourth column. Because I've already selected a 0 in the top row, I can't select it in the top row again for the second column, so I'd have to choose the bottom 0 here. And then last, the only row that I've got left with a 0 in it is the second one down, so that's the 0 I'd have to choose in the fourth column along. So that's my pattern of zeros, where there's only one in each row or column. That pattern of zeros is also the optimal solution in the original matrix, and you may remember back to our previous trial and error solution, we did find that the C swimmer should do backstroke, D swimmer should do breaststroke, the A swimmer should do butterfly, and the B swimmer should do freestyle, which is what we found, but this is, well, it should be a quicker method once you've gotten the hang of it, rather than doing trial and error. Alright, so hopefully that helps you out, and I will see you in the next video.